Hi everybody, this is going to be on section 14.5. The title of that is Curvature and the Normal Vector, but actually what they have done in this version of the text is combine two previous chapters into one. So there's actually a lot of material in here. 14.5 has two chapters worth previously. So we'll talk about the normal vector, but there's also something called the binormal vector. It mentions curvature in the title of this, but there's also a thing called torsion that we'll look at. So I want to kind of give you a framework for all of this first, which is I'm going to try to illustrate using this flexible ruler that I have from a previous life. So I'm going to try to hold it relatively steady, and you imagine that's a space curve, okay? What we want to do is think about a point that's moving along this curve, and if you were on that point, let's think of it as a vehicle, right? Maybe it's an airplane or a submarine or something that's able to move in a three-dimensional way. If you were on that point, you'd like to have a local coordinate system. So you'd like to have a sort of an X, Y, and Z system that goes with your vehicle, and as you move along the curve, you carry this coordinate frame with you. Now, you wouldn't want to just have it arbitrarily oriented. There's some things that just you would prefer, I think, in such a coordinate system. Like, wouldn't it be nice if the x-axis lined up with your motion? And that's what one of the things we'll do is make one of the axes of this. It's called the Frenet frame, or TNB is another way people talk about it. That's three initials, T, N, and B. Anyway, well, there's a way to make it so that the x-axis, or the first coordinate, follows the forward direction as you move along the curve. The y, it always points in the direction of curvature, which means when you have a moment, wait, I should tilt it so you guys can see the change in curvature. See how it's bending to the left here and then bending to the right there? That means the y coordinate has to suddenly flip around to that way. And I can't move through my own hand, but then if I've got another change in thing, so it flips that way. The y always points towards the inside of the curve. That's the way we'll make that thing work out. And then z, the third direction is just perpendicular to the other two, so that one's relatively easy to deal with. In this setup, there are two numbers scalars now. So we mentioned three vectors. Those things are called t, n, and b respectively. So t is tangential to the curve, n is the one that points towards the inside of the curve when you're going around bends, and that's normal vector, and then the other one, b, is the binormal vector. Those three vectors are sort of things that each of them is a function of where you are along the curve, but there's two other things that are numerics that let us think about the curve. One of them is called the curvature. So let's try to make a curve on this guy that's pretty intense versus a curve back here that's not so intense. So this is lightly curved, and this is strongly curved in here. Now, what is that? Well, one way to think about curvature is to imagine a circle. It would be a pretty big diameter circle right in here that would just kiss the curve. It would be tangent to the curve, but also it would agree to the second derivative of the curve. We'd have a large radius circle here, but in here we'd have a really small radius circle. So there's a little backwardsness there, that the large radius means relatively small curvature. And small radius, this one has a radius of about 1 inch. Well, that means a lot of curvature. If you think about the radius of curvature getting, well, let's look at this section in here. If I unbend it slowly, I'm making the radius grow. The center of the circle was here. Now, as I make it straighter and straighter and straighter, what's happened is the center of the circle just went off to infinity. I mean, once you get a straight line, you've got an infinite radius of curvature. The the radius is infinity, but that's actually the reciprocal of the thing we call the curvature. So we say a straight line has zero curvature, which I think makes sense. So, all right, if you've got a space curve, a 3D, a vector function of say time, and it's got curvature to it. That is this. We call this thing kappa, the Greek letter for. Well, I don't know. I guess if I was trying to spell curvature in Greek, I'd start with a K. Anyway, if you've got a space curve that has curvature, that's cool because you go from something with zero curvature is a straight line. That's just straight line motion. You can have plenty of space curves that are straight line motion, but when you add curvature, you get the ability to move around in a plane. So you go from 1D to 2D when you put in curvature. That second scalar I was talking about that we'll need to discuss is called torsion. And torsion physically actually means a twisting. And if I twist this curve that was bent this way, and then was bent in the other direction, but if I have a twist in between them, you see how the object has now become truly 3D? This will not lay flat in a plane anymore. It's just, it doesn't. So one way to think of it is if you had something in the plane and then you pull it out of the plane, you can't avoid putting a twist in there. I don't know if you can see what that was doing, but as I lifted the one, a portion of it in the plane, pull another portion of it out of the plane, I have to create a twist to the curve. That's, I think, why the concept is literally called torsion. But if you don't have torsion, you will have something that just lays flat in the plane. With torsion, you can get truly three-dimensional things. For instance, the helix that we did once that goes up along a spiral, right? Well, that's got torsion. It's got curvature as well. Do you remember the spiral that we drew that just spirals out and stays in the plane? Plenty of curvature, but no torsion. You can tell because it's laying flat in the plane. All right, so that's sort of an informal intro to these things. To get started on this stuff in a more formalized way, we'll first need to introduce the unit tangent vector. So we're going to start with a space curve, a vector function of a parameter t. You don't really need, I won't in any of this need the coordinates or the components of this vector, so we'll just keep calling it r of t. We don't need to talk about the x, y, and z pieces of it. I want to mention, before I get any further, that we will often prefer to think of this as a function of position along the curve. So we may use r of s. In fact, we will often think about it as r of s, but we actually just need to get facile with going back and forth between these two things. So this is usually thought of as a time parameter. This s is a space parameter, or well, literally arc length, position along the curve. Why do we do that? Well, it turns out the two things are really pretty easy to switch back and forth between. If I know what t is, I can always use the function s of t to get s, right? So let me put it a different way. If I have a position function that's given as a function of arc length, but I know how to translate time into arc length, well, this s of t, this function allows me to write r of s of t. And that just means in the end, I've got a function r that's a function of t, a vector r that's a function of t. I've got this kind of thing. On the other hand, if I just had r of t, think of that as the primary guy, but I wanted to convert it into r of s, well, I just need the inverse of this function. When you're just using the name of the function as the output variable, there's a cute way to think about finding the inverse. You just write t of s. S of t is the function, t of s is the inverse. It's kind of cool, but what does that mean? That means that you could take r of t here, that version of things, and compose it with t of s, and you've converted it to that version of things. So the point really is that the parameterization isn't terribly important, but the arc length parameterization is the one that theoretically is going to help us the most. So we'll think about this one, but we'll be able to quickly convert to that one if we need it. And you'll see that a lot of the calculations come out the same regardless of which parameterization you use. Okay, so given that we've got r of t, let me just sort of box off this whole discussion about the arc length parameter for now. Think that we're dealing with r of t. There's a space curve. I want to go have a little tight section in there, but mostly it's not terribly strongly curved. We will talk about the velocity vector along that curve, which is going to be just r prime, the derivative with respect to t. And that first component of this frame I was talking about, well, that's going to be defined as, it's called t, capital T though. What you do to get capital T is take the velocity vector and then scale it by its own length so that you end up with a unit vector. Okay? That is, you take v of t and divide it by the length of v of t. Darn, I just noticed I made a slight mess up here. You notice how I haven't mentioned the fact that this is a function of what time it is? Well, it clearly is, right? If you think about in here, I would have a little unit tangent vector pointing that way, but over here, at a different time, I'd have a little unit tangent vector pointing that way. And here, I'd have one that was pointing that way. They're changing with time. So I hate to erase, but let's do that. Let's call it t of t. That is big T, the tangent vector, a function of little t, the time. But this is how we define it. Okay. Actually, this picture almost does the trick for me in terms of one thing I wanted to point out to you. Would you say, I think it's true that these 2 points are a relatively short distance apart. The length along the curve is about 1 inch there. Let me go over to this point and draw another spot on it that's about 1 inch away and draw a tangent vector there. Do you notice something about the relative differences between the tangent vectors? Here, the tangent vector has barely moved as we go from there to there. Actually, neither one of them look like they're quite tangent to the curve, but that's just the sketch. But on the other hand, here, in the place where the curvature is large, notice how much the tangent vector has changed. It was pointing down and to the right, and over here it's pointing down and to the left. I mean, it's almost 90 degrees, isn't it? So, do you notice how when the curvature is small, moving a small amount along the curve creates a small change in the tangent vector's direction? But when the curvature is large, moving a small amount along the curve makes a big impact on the tangent vector's direction. That's meant to just justify the definition we make for the curvature, which is just this. You take the derivative of this t, except you want to take the derivative with respect to the arc length parameter. Why do I want us to do it with respect to arc length? Let me give you a different sketch. Let's try to do the same curve, more or less, right? But suppose here was time equals 0, and here was time equals 1. And then time equals 2 is here, time equals 3 is here. I'm going through the curvy part really slowly. Then I accelerate coming out of the curve, and then you know, that's actually how you would drive a thing like that, right? If you had one of these windy turns like that, you would come in at full speed, slow way down, and go through the bendy part, and then take off. Well, that means, like over here, I've got fairly large change in direction of the tangent vector, but that's happening in 1 second. Whereas in here, even in the bendy part of the curve, I've got maybe a change of 30 degrees because time isn't the same as distance. So we look at this and say, yeah, it's really bent, but if you're crawling as you go through here, your tangent vector isn't really changing that quickly with respect to time. So here's the definition then. The curvature, kappa, I should give you a name. Just try to draw a fancy looking K. It's actually not as tall as a regular K in the Latin alphabet, but sort of the same height as a lowercase letter, and it's a little bit curly looking. Anyway, kappa is going to be a function of s, where you are along the curve, not what time it is. So if I was parameterizing this curve by arc length, then it would be 0 to 1 to 2 to 3. You would have evenly spaced things in terms of the distance along the curve. Anyway, this kappa is defined as the derivative of the tangent vector as with respect to arc length. That's actually a function, dt ds. T of s, the derivative, maybe I should say this one other way. You think of it as d over ds of t of s. All right. But what I actually do almost all the time is just stop writing the parameter, right? Just call it dt ds. If you know that you're dealing with something that's a function of arc length, in fact everything floating around is a function of arc length, then you can just stop writing the of whatever's on it, and everybody will understand what you mean. In fact, you may have to remind yourself, hey, wait a minute, these guys are all functions, but it makes what you have to write a little bit easier, right? You just say k is dt ds. Which is probably how I'll do it most of the time. There will be occasions though when we do need to sort of jump back or step back and think, okay, wait a minute, this is a function of position or a function of time, what's going on there? Well, here's a problem. Usually, I think we saw this in practice, in fact, usually this arc length thing, you can't figure it out. You can't do the integral that would get you the arc length parameterization, that would get you that function s of t I was talking about. So if you want to have kappa, which is defined this way as the space derivative of the tangent vector, but what you've got is a tangent vector that's expressed as a function of time. So rather than kappa of s, let's see if we can figure out what kappa of t is. Well, actually, that's just the chain rule. And this is a place where where the Leibniz notation is actually way easier than the Newton style notation. You remember let me just take a second and remind you of what the chain rule looks like back from Calc 1. You had some f of g of, let's make it t, so we'll still be in the same realm we're in now. And you wanted the time derivative of that. Well, you took the derivative of the outer function and you applied it to the inner function, and then you also multiplied by the derivative of the inner function. And that, I don't know, that looked kind of complicated, but when you make this the same sort of computation in the chain rule that you do well, that we're doing here using the Leibniz notation, it's actually way easier. Suppose we had something like, y is a function of u, and u is a different function of t. And so what I'm really looking for is the composition to get that y of u of t, right? So the derivative of that composition is just dy du times du dt. Because the Leibniz notation just deals with the variables involved rather than the names of the functions. And that just looks cleaner. I mean, what really happens is the derivative of this composition now, it just looks like you can cancel the du's. The reason Leibniz used this dy over dx or dx over dt kind of style notation is that algebraically it does follow the same rules that cancellation does. It's really not the same thing because both of these are defined as limits, but you can just behave as though you could cancel. All right, that was just a reminder. Let's erase that. Sorry if you can always pause the video and write that down if you need to. What I wanted to do was sort of figure out how to get kappa as a function of t. Well, I think of that as the original kappa that was a function of s, but composed with s of t. So the derivative, what am I talking about, derivative? Sorry, wrong way to say this. Not kappa, but we were talking about t as a function of s, and we need to take the derivative, yeah? So I'm going to, kappa of t is what I'm interested in. To do that, here, let's just write a colon. To do that, what we need to do is think about t as a function of s, kind of morphing into t as a function of s, which is itself a function of little t. Well, let's just write down the Leibniz version of things when we take the derivatives of both of these. This one is dt ds, d cap t. Oh, vector hat's missing all over the place here. Dt ds. And this one is dt ds times ds dt. You just, when you're having to recover what this is, you just know that you're going to have a ds that cancels with this, so that you end up with dt dt. Shouldn't have said it equals it, but rather it turns into it in this version of things. Cool. What is this in the end? Well, that cancellation I keep talking about happens, and you end up with dt over dt. The time rate of change of the tangent vector as you move along the curve. So what this says to you, if you look at just this last part, let me draw a box around this, that's a very important relationship. What it says to you is dt dt and dt ds, both of those are rates of change of the tangent vector, one with respect to arc length, one with respect to time. They're proportional to one another. And the constant of proportionality is this guy, ds dt. Well, do you recognize what ds dt is? S is arc length, or position along the curve. T is time. That's the rate of change of position with respect to time. You want to say that in a less fancy way? That's speed. Or another way we often write it is, it's the length of the velocity vector. But speed in the end. Okay, so that gives us a way to really express kappa in terms of t. Just solve this for this guy right here is kappa. Well, technically I think it's the absolute value of that. Let me look in the notes here. Yeah, the notes have it as an absolute value. Why did I do that? Because the kappa should be just a raw number, right? TDS is in fact a vector. That is, had that same issue up here. It should be the length of these things. Right. All right. So I'm gonna give you how to write kappa figure out kappa as in terms of the parameter t. It's just this. Kappa is equal to, take the derivative of the tangent vector, the expression for the tangent vector with respect to time, but you've got to fix it up because of this factor of the speed. And it turns out what we're really doing is we need to divide both sides by the speed. So I'll write it as 1 over the length of the velocity vector. Let's do some quick examples of calculating kappa for situations that are almost too simple. I have that magnet there. Suppose we are working on a line. The position vector will be something that consists of 3 linear expressions, like 3 plus t, 2 minus t, and 1 plus 2t. Just to make it interesting. So we can figure out the velocity vector as a function of time. It's going to be 0 plus, that'll be a 1 in the x position, it'll be a minus 1 in the y position, and it'll be a 2 in the z position. The velocity vector's length, this is the speed, as we follow this parameterization, would be the square root of the sum of the squares, which in this case is square root of 6. 4 plus 1 plus 1, right? Root 6, okay. The tangent vector, the expression for the tangent vector as a function of time now, is take the velocity vector and divide by its length. So you get, well, let's write it as 1 over root 6 times that velocity vector. And then the curvature, that's a really poor kappa. I'm going to fix that one. The curvature, using this expression, we take the derivative of our tangent vector with respect to time, and we divide it by the speed. But this is a constant vector, right? I keep forgetting to put the absolute values around these. We want the lengths of these vectors, not the vectors themselves. Oh, my bad. This thing, though, well, I mean, the derivative of t, which is constant, is 0. It's a 0 vector. When we take its length, we get 0, and it doesn't matter if we multiply by 1 over v, we still get 0. I think that was something I said in the intro. If you've got a straight line motion, there's no curvature. Even if the straight line motion is not at a fixed speed. So this was particularly nice straight line motion. We're moving along at, well, speed of root 6, never changing our speed. I could change that, and I think it might be instructive for us to change that by putting like all of these t's all these t's will become t squareds. Now I'm not moving in a straight line fashion anymore. What's my derivative? 2t. I'm still moving in a straight line. It's just that I'm not doing it at constant speed. The velocity is 2t minus 2t and 4t. And that means the acceleration is a constant vector, but the velocity is not. What would we get for our tangent vector now? Well, I need the length of this thing, and the length of this thing now involves the parameter t. So, well, maybe let's do a separate calculation of that. What is the speed? As a function of time along this curve, it'll be the square root of the sum of the squares, which are 4t squared plus 4t squared plus 16t squared. I think that's 32, right? 4 and 4 is 8. No, it's not. It's 24. And then, in fact, you can just turn that into t times root 24. So the velocity is going up as t goes up. The bigger t gets, the bigger the velocity vector. Sorry, the velocity vector gets bigger, but I was actually pointing at the speed. As the t goes higher, the speed gets higher. We're accelerating it along this line. But we can still work out the curvature and see that indeed the curvature of straight line motion is 0. So for that we need to work out what's the tangent vector. It's going to be your velocity vector divided by the velocity vector's length. I'll write it as a fraction involving a vector because you can do this. And it makes it a little bit clearer how the cancellation works. You see how the t in the bottom is going to cancel with all the t's that are in that, and you end up with a constant vector. It's not as nice as the one before, but it's okay. Let's stop doing the writing it as a compound, a fraction with a vector in the top and a number in the bottom. That feels weird. So 2 minus 2 and 4. With root 24, 1 over root 24 out front. So that's your tangent vector, and can you tell from that that its derivative is 0? So this vector is going to be 0, and dividing by the speed isn't going to matter. Kappa will be 0. Cool. Well, I've got here in my notes that we should do another example where we figure out kappa for motion in a circle. But that's in the book. And maybe I'll ask you to look at it. I believe that's example 2 in section 14.5. There's a really interesting little section that they go through kind of quickly after this, after examples of calculating the actual curvature, which is to give you a whole different way to compute the curvature. It doesn't involve finding the tangent vector at all. The formula is this, that you can figure out the curvature by taking the cross product of v and a, that's the velocity and the acceleration vectors, and you just divide by the speed. Can't fix that. The speed cubed. I'm constantly forgetting the lengths part, because this is supposed to end up being a number. The way I had originally written it without the absolute values, that would be a vector. So figure out the cross product of velocity and acceleration. That's not terribly hard. And then figure out the speed, the length of this guy divided by the speed cubed. Interesting little alternate formula. Let's see how it gets derived. In the notes I've made this observation that v of t is I don't have the of t's in anything in here, but they all depend on t. V of t is the derivative of the position, and a of t is the second derivative of the position. So you could say it's v of t's derivative, or you could say it's r of t's second derivative. Both equivalent. Well, the starting point for this alternate formula is going to be this observation. It's a kind of silly one, um, but sometimes it's amazing how much stuff you can get out of a silly observation. It's just this, that you can think of the velocity vector as being the speed times the tangent vector. The way this normally worked is you define the tangent vector by taking the velocity vector and dividing by the speed. But just move things around and we've solved it for the velocity vector. So velocity is equal to speed times this unit tangent vector. This has the same direction as v does, and that's v's length. So yeah, this is going to be the same vector. Why is that useful? Well, you can get another way to write acceleration from that, because acceleration is the derivative of v, and we just wrote v like this. So we get a is equal to, let's do it the Leibniz notation, d by dt of this thing, the speed times the tangent vector. Well, that's a product. That's a scalar product, right? We have a scalar times a vector, so that's I don't mean it's dot product, but a constant multiplier product, right? And in a case, the product rule applies. So the acceleration can be re-expressed as, take the time derivative of speed by d by dt of length of v, and times it by t. I want you to be sure that the derivative applies to that one, and that's unchanged. Plus, leave the speed part unchanged and take the time derivative of t. Okay. Well, I guess that's okay. That's just an odd way to write A, I suppose. But look what you get when you use that in calculating V cross A, because the formula I told you we're going to come up with involves V cross A. So let's look what V cross A is. Well, it's V crossed with the thing that I just wrote down above, which is d by dt of speed. Now, that's an interesting thing. If you take the time derivative of speed, you know what you're going to get? That's acceleration along the curve, sort of in the direction of the curve, but we'll come back to that. The other piece of it is speed times the time derivative of t. I just have room to fit this on the board. So the vector v crossed with this thing, which is a sum. And one of the rules we've learned about how cross products work is that there's a distributive rule. I'm going to erase everything down to the last thing I wrote so that we can copy that in. And then maybe I'll erase that. All right. V cross A looks like that, so let's distribute. We'll have V crossed with this plus V crossed with that. V vector crossed with time derivative of V, time derivative of speed, times t. That's the V across the first element of the sum. And then we will have the second thing will be V crossed with the second piece here. Length of the velocity vector times d by dt of t. Just barely made it. And there's a cool observation you can make at this point. That's the velocity vector, And I don't even care what this is because it's a scalar. And the hat's not on this one, which is my mistake, but that's a vector. And what do you know about the directions of the tangent vector and the velocity vector? Well, the tangent vector is just, you get the tangent vector by taking the velocity vector and scaling it till you get length 1. So this is a length 1 vector that points in the same direction as that guy does. And we're going to scale it by something, but the real point here is that these two things are parallel. They point in the same direction. So what happens when you take the cross product of two vectors that are parallel? You get a zero vector. So this whole thing simplifies to just the second bit. It's v crossed with the speed times the time derivative of the tangent. Now, okay, here's an interesting observation. This v here could be rewritten, like we did before, as the speed times the tangent vector. So you take length of v times the tangent vector, and we're crossing that with length of v times the derivative of the tangent vector. Let's actually write it as Leibniz would, dt over dt. Well, what's up with that? Those vectors, this one and this one, are perpendicular to each other. Why do I know that? Well, remember when we were doing motion, in the beginning stuff in motion in space, I pointed out that if you had a position vector that was constrained to lie either on a circle or on a sphere, in 3D it's on a sphere, if the length of the position vector is fixed, when you take its derivative, you'll get something that's perpendicular to it. That is, if your motion is on a sphere, your velocity vectors are all perpendicular to radial vectors. But that applies here, because t literally is motion on a sphere. It's a sphere of radius 1, because that vector has a unit length. And dt is its velocity, or if we think of this as a position, that's the derivative is its velocity. So these guys are perpendicular. So let me just point that out. That one and that one are perp. So when you go to figure out the cross product, the length of the cross product is really easy because the two directions are orthogonal. And the sizes of them are both, oh well, we don't know what the size of that guy is, but yeah, but this, we can actually compute the length of the cross product from this real easy. All right, yeah, so the whole thing we've been working on is the cross product of v and a, right, the velocity and the acceleration vectors. And now I'm ready to say what the length of that is. And again, those guys are perpendicular to each other. I don't know how big this one is. I know that one's unit length. But the parallelogram is going to have area. Well, the parallelogram is actually going to be a rectangle with the speed in one direction and the speed times the length of this guy in the other direction. If you want, you can go ahead and work this out through the. Well, here's how you do it. You use the formula for the cross product's length, which is the product of the two lengths of the two vectors times the sine of the angle between them. The saying these two things have length are perpendicular is the same thing as saying that theta there is equal to 90 degrees, or pi over 2. So that number is 1. Right, so length of v cross a is what we got above, the length of v times the length of v, so length of v squared, times the length of dt dt. But that's almost perfect because that dt dt's length is kappa times the speed. That was something that got erased a little while ago, but one more, well, let me just put a point at that from here, I suppose. That piece there, you may have noticed the quick edit I just did there. I had a brain failure and I had to go back and look it up, but we had previously seen kappa could be written as the length of dt times 1 over v, which means just solve it for the length of this, that length of dt tangent vector with respect to time is going to be the speed times kappa. So this guy here is, well, this whole expression is the length of the velocity vector, that's the speed, cubed times kappa. Weird looking kappa. Right, so this is it. This is the thing that gets us our alternative formula, because you just solve it for kappa. Kappa times v cubed, speed cubed, is v cross a's length. Just divide everything by the speed cubed and you've got kappa. Let me write it one more time over here on the side. Kappa can be written as the length of this cross product of velocity and acceleration divided by the speed to the third power, which some people prefer. I'm not sure if I like that one best. Often it's for my purposes, it's easier to just use the definition and calculate what is dt/ds, because that's what kappa is too. Okay, next page. Okay, so let's put this alternative formula to work. This is example 3 in section 14.5. So you can always go back and look through it in the book to see the approach to it. But what we're going to do here is figure out kappa along a parabola using this alternative approach, v cross a over v cubed. So this is actually motion in the plane, but that's okay because, you know, curvature really is mostly about generating plane motion. R as a function of t is going to be this vector, t comma t squared comma 0. So x and t are the same, and so this is really the curve x comma x squared, or y is equal to x squared. It's a parabola in the xy plane, and the z coordinate is 0, so it's literally in that flat plane. Okay, velocity along this curve is 1, 2t, 0. Right? Just taking derivatives, and acceleration along that curve is 0, 2, 0. Let's figure out what v cross a is. Well, after all, it's that determinant. We've done a bunch before of I, J, K, and the components of v are 1, 2t, and 0. The components of a are 0, 2, and 0. Take that determinant. I'm gonna do this pretty quickly because most of the components are 0. Like the I component has 2t times 0 minus 0 times 2, so that's 0. The J component also involves 0 times things, and so it's plus or minus 0, that's 0. It's only the K component that survives, and it's only the 1 times 2 because you're subtracting minus 2t times 0, so you get 2. So the length of v cross a is 2. Oh, wait, I got one more thing I need to do. What's the velocity's length? What's the speed? I can maybe do this just on the side here. The length of v is going to be square root of the sum of the squares, which is square root of 1 plus 4t squared. Okay. So then now we can use that alternative formula to figure out kappa. V cross A's length, well, let me just copy it first. V cross A divided by V cubed. Yep, so V cross A was, length of it was 2, and the thing in the bottom is the cube of that, square root of 1 plus 4t squared. If you run through this in the book, I believe the difference between what the book did and what I have done is they allowed a multiplier in here, so they could do it a slightly more generality with a constant time, so y equals a constant times x squared. I really didn't like it because the multiplier they used was a, and we were already dealing with a's. They're supposed to be vectors. Sorry. So I avoided it, just did it for the simple parabola y equals x squared, but you can do it in more generality if you like. They also end up writing this as a fractional power, so it's something over something to the 3 halves power. 1 plus 4t squared. Because the cube of a square root is the same as 3 halves, right? Okay, so we're ready to move on to the second vector. So all this time so far, we've just got the t vector involved. Now we want to get the n vector, the unit normal. Well, the unit normal actually turns out to be relatively quick because we've already seen this observation that t being a unit vector, when you take its time derivative, you're going to get something that's perpendicular to it. And that's all we really want, right? We've got a tangent vector. Can we find something that's perpendicular to it? Great, the derivative works. Now the problem is the derivative may have different lengths. It might point the wrong way, it may point the way we want, but in any case, it's, I guess pointing the wrong way isn't an issue, but the length of it could be whatever. So we are going to take that derivative and scale it appropriately until we get a unit vector. All right, so the definition of the normal vector, sorry, probably should have headed this up with the name of the thing. They call it the principal unit normal. Don't know why principal, but for some reason that word is used with the unit normal vector and not with the tangent vector. I would like to call it the principal tangent vector. Maybe there's just the one. You could maybe have multiple choices for the n. I suppose you could. Yeah, there's lots of other vectors that are perpendicular to t, but this one makes good sense. So it's defined as the space derivative of the tangent vector. Not quite, because that thing might have arbitrary length, so we divide that thing by its length. And here's a funny thing. It doesn't matter whether I take a time derivative or a space derivative or arc length derivative, because I will get something perpendicular. The time derivative and the space derivative point in the same direction. They have different lengths, but that's cool because we're dividing by their lengths to get something that's of unit length. So it's exactly the same thing to do it with respect to time. You can take dt, dt, d big T, d little t, and divide that by its length, d, t, dt. That's kind of fun. Now that we've got both the tangential direction and the normal direction, we can stop and do something that's kind of cool about planar motion. And let me just describe this planar motion issue to you in terms of driving a car, because I think almost everybody will have had this experience. There's two ways that you can be accelerated when you're in a car. One of them comes from somebody stomps on the gas or stomps on the brake, right? And that's in the direction of motion. You either get pressed back into your seat or you lurch forward against your safety belt. But there's another way that they can accelerate, which is laterally. They can turn the wheel. The car makes a curving motion. There's centripetal force, they call it, that acts on you. It makes you feel like you're bending out to the side of the big push to the outside of the curve. Those two different senses. And wait, I should mention, you really, at any time you're getting a combination of those. Like if you're braking hard while you're entering into a turn, you're going to be forced against your seat belts, but also pushed away from the center of the curve. So yeah, you can have combinations of those two things. And what we're going to do actually is write our acceleration vector in this kind of a form. It can be written as something times the tangent, a component in the tangent direction, plus something times the normal. And those somethings are scalars now. They're called a sub t and a sub n. So if we do this, this is called the tangential component of acceleration. And the other guy is called the normal component. So I'd like to sort of see how to compute those. First off, I'm going to write the length of the velocity vector as ds dt, because that's what it is. So just a remark on the side. The length of for the most part here, we're going to write this as the time derivative of displacement along the curve, ds dt. And actually that gives us a way to re-express the velocity vector, which we had previously done as this thing, the length of velocity times the tangent vector. So our velocity may be written as ds dt, whatever that is, times the unit tangent vector. And then we're going to do the same thing we did a little bit ago while we were doing the alternate, the derivation of the alternate formula for the curvature, which is take that thing and take its derivative using the product rule. And that'll get us the acceleration, right? So that is, the acceleration can be written as the time derivative of the thing right above us. ds dt times t. But this scalar multiple times a vector requires the product rule to do it. So we get d by dt of ds dt times t plus ds dt times d by dt, whoops, wrong t, trying to use the capital T there, that doesn't belong, d by dt of t, there we go. And as usual, I forget vector arrows as I go, so that's it. Well, what is the time derivative of ds dt? It's already in the Leibniz notation, so we're asking about the second derivative with respect to time of s. And that's written, and I hope you recall this, that you write d squared s dt squared for the second derivative. So that's the second derivative of position along the curve times t. And then, well, we've got, what do we have there? ds dt times dt dt. careful that I've got dt and little dt. This isn't the kind of thing where you can cancel anybody, right? That's interesting though, isn't it? What's dt over dt? It's very close to being the normal vector. How do we turn it into the normal vector? Well, let me turn it into the normal vector in a Leibniz style calculation. Okay, this part we'll just have to copy in d squared s dt squared times t, and ds dt is fine. But I'm going to break that up as if it were we're coming from one of those Leibniz rule composition calculations. Think of it as dt ds times ds dt. Now the length of dt ds is the curvature. So that's basic. That vector right there is actually the curvature times the normal vector. And then we've got 2 copies of the speed on that side. All right, that means, do I have enough space to fit it in? Not really. Let me go to the top of the board and we'll erase some of the setup we began with. So what we've got there is that the acceleration vector has been written as the second derivative, I'm not liking my d there, the second derivative of arc length with respect to time times the tangent vector plus, this is actually kappa times n, and we've got 2 copies of the speed, so we've got the square of our speed times kappa times the normal vector. And that actually, those actually are the components that I was talking about. This guy right here, that's a sub t, the tangential component of acceleration. And this product is a sub n. Now that physically tells you some interesting stuff. The acceleration you feel sideways depends on 2 things: how curved the road is and the square of your speed. So if you go through the same curve at twice the speed, you're going to experience 4 times the acceleration. This is why they pay race car drivers the big bucks, because there's a fine line between making the curve and having your tires completely lose traction because the force that's required of them is much too great and break off and you end up off the road. So this causes a fairly sensitive dependence on speed. You've got to get the right amount of speed as you go through a curve. It's also a good lesson for beginning drivers. Slow down before you turn, because things can go really ugly when you don't. Especially lately, I've been driving a Jeep, and if you try to give it too much lateral acceleration, it rolls over, which is not a fun thing to do. I have a nephew who still has pins in his bones because of that kind of deal. Okay, so let me check my notes here. Great, we got through that. One last thing though, which is to put all this in action for a particular example. I'm going to use the same example we did a second ago, motion along a parabola, because again, if we're only doing with this much of it, the normal vector and the tangent vector and things like that, your motion in a plane is all that will ever result from that. We're going to need torsion and eventually the binormal vector to get true 3-dimensional motion. So this isn't really as much of a cheat as it may seem. R of t is going to be t squared 0. And I want to work out, basically everything. I want to figure out velocity, acceleration, tangents, the components of the acceleration, etc. So let's first get velocity. That's easy, just take the derivative of this and you get 1, 2t, 0. And acceleration is 0, 2, 0. I think we did these a minute ago. Let's work out the tangent vector as a function of time. That's our velocity divided by the velocity's length, which is 1 over the square root of 1 plus 4t squared. Remember we got that in the last one, that's why I'm rushing it a bit, times the velocity, 1, 2t, 0. Now, the normal vector is a little hard to get at, but I'm going to do a quick cheat for us here, which is, think about it geometrically. In the xy plane, what we're dealing with is a parabola, right? Let's just think about the positive branch of the parabola. So I'm at a point on here whose coordinates are t comma t squared, when the position vector is t squared. The tangent vector points along the curve in the direction of increasing time. So that's t. And the normal vector is supposed to point towards the inside of the curve, and it's supposed to be orthogonal to that. So we can actually produce for ourselves a vector that's orthogonal to this t pretty easily. You see, t's components are 1 and 2t. Yeah? I'm just drawing this in the flat, so we're ignoring the z. Well, then what are the components of that orthogonal vector? Looks like the x component is negative, and it's the longer one, the 2t. This guy is minus 2t, comma 1, which you can really check easily. What's the dot product of those two things? So that's our normal. Of course, actually, that's not quite right, because both of them need to be divided by that square root of 1 plus 4t squared. But, as far as the direction of them is concerned, we needed to produce orthogonality. So, by a little bit of a cheat, the normal vector as a function of time is 1 over root 1 plus 4t squared times minus 2t, 1, 0. All right, I can do a projection into the direction of the tangent vector to figure out the tangential component of acceleration. Look at me, badness, never writing my vector hats when I'm supposed to. So I can figure out projections, a sub t. That is the projection of the vector A into the direction of t. And that scalar, the ugly part of that scalar, doesn't change the direction of it. So I'm just going to write the vector part. I want to take the projection in the 1, 2t, 0 direction of our acceleration, which is 0, 2, 0. Remember doing the vector projection? You take the dot product and then you divide by the length of this one. So the dot product is 0 plus 2 times 2t, 4t plus 0. And we've done the length of that one a bunch. Square root of 1 plus 4t squared. So that's one way to get one of these components, just project into the direction of the other. I want to get you the normal component by a different method, because it's kind of cool. You see, we know the normal acceleration is the curvature times the square of the speed. I guess I gotta get some room to write, so I'm gonna have to erase some stuff. For the normal component, a sub n, use that a sub n is kappa times speed squared. And let's go one more step. Kappa, remember the alternate formula for kappa? It was v cross a over speed cubed. Which means a sub n is this times v squared, the v cubed in the bottom, the v squared in the top. That's gonna let us get a sub n is equal to v cross a divided by v, the length of v cross a divided by v. Right. I probably want to try to save this calculation of a sub t because we're going to need that in a second. V cross a would, I think, didn't I just do this? It was I, j, k, 1, 2t, 0, and 0, 2, 0. Yeah, it ended up being 0 in the first two components and 2 in the last, right? Remember doing that? So I probably didn't need to do this, I just couldn't quite remember myself. So a sub n is equal to the length of that, which is 2, divided by the length of the velocity, which is that familiar square root of 1 plus 4t squared. Yeah. So we should be able to verify that the acceleration, so let me just write this question parenthetically, is the acceleration vector actually equal to the a sub t times the tangent vector plus a sub n times the normal vector? We've gotten a bunch of these things via various methods. All right, let's, now I can get, no, I really want to remember that, which is a sub t. Okay, it's the first number I've got. So 4t over that square root of 1 plus 4t squared times the tangent vector. Good, I wrote it in my notes. It's a 1, 2t, 0 over that same radical. Maybe I can't get rid of this stuff. So that's a sub t, that's t. And a sub n, we did it. A sub n is this expression, right? 2 over square root of 1 plus 4t squared. And n, gosh, what was n? Oh, I remember, that's the one I kind of cheated and used geometry to figure out what it was. It's minus 2t, comma 1, comma 0, divided by, again, that's square root of 1 plus 4t squared. The speed is appearing in multiple places. All right, so multiply everything together and add it all up. You notice that what's going to happen in the denominators, they're both going to have this thing without the radical anymore. So let's sort of write it all over one big 1 plus 4t squared. 4t times this vector gives us 4t, 8t. Oh, I'm sorry, 8t squared. 4t times 2t, 8t squared, and 0. 2 times that vector gets me minus 4t, comma 2, comma 0. This is unfortunate that I don't have quite enough room to get to the punchline here. But you see what's going to happen in the x coordinates? They're going to go away. The y coordinates, it's 8t squared plus 2, and the z coordinates, 0. Yeah, I can just squeeze it in here. Upstairs, we have a vector with 0 in the x spot, 8t squared plus plus 2 in the y slot, and 0 in the z slot, and 1 plus 4t squared downstairs. What's that supposed to be? It's supposed to be our acceleration vector, which is actually right there, 0, 2, 0. Check out that it is. 8t squared plus 2. If I just written this 1 plus 4t squared in the other order, you might see the cancellation better. But the y component of that vector in the top is the double of the number we're dividing by. So yeah, it did all work out. Just, you know, I'm a fan of calculating things in multiple ways, and then you have multiple ways to cross-check yourself. But, you know, having that thing actually come out to what it was supposed to be, the actual acceleration is great. All right, so I'm going to do a second video that has the stuff about the binormal vector and torsion in it. So that's it for this one.